Hello dear students, welcome to a new lecture. In this lecture also we are going to learn something new and fun. The topic of discussion today is elements of Earth's magnetism. Yes, you know already that Earth produces magnetic field around it, similar to a bar magnet we can say. And we know this because we have seen the magnetic needle of a compass deflect and orient in the direction of north-south, right? However, we rotate the compass, the magnetic needle will be orienting in roughly in the north-south direction, right? So that is one proof or evidence that we have that Earth produces magnetic field. Okay, you can do that even by suspending a bar magnet. If you tie a thread to a bar magnet and if you suspend it, then what will happen? Yes, it will orient in some direction which will be actually close to the north-south direction. Okay, now we have other proofs also that Earth produces magnetic field. Can you think of any? Yes, if you take a magnetic material like iron, you take an iron bar, which is a magnetic material. If you bury it inside the Earth's surface and keep it there for some time, you remove it later, you will find that it has been magnetized or it became a magnet. How does this happen? It happens because Earth's magnetic field induces magnetism in this magnetic material. Previously, it was just a magnetic material, not a magnet, remember? But when you bury it and keep it there for some time and you remove it, it becomes a magnet. So this is called induced magnetism. And who induced this magnetism? Earth, because of its magnetic field. So this is another proof that Earth produces magnetic field around it. Another proof you want. Okay, I have another one for you. If you keep a bar magnet, okay, you know that bar magnet is already a magnet. It has north pole and south pole. So there will be magnetic field lines originating from the north and going into the south. You cannot say originating and terminating actually, because the magnetic field lines continue inside the magnet also. Suppose this is a magnet and this is the north pole and this is the south pole. So the magnetic field lines will be coming out of the north pole and it will be going into the south pole, and inside the magnet also the magnetic field lines will be continuing. It's a closed loop. So yes, we already knew this. Why are you telling this to make us understand the Earth's magnetism? The thing is, if this bar magnet, if you bring a compass near this, it will deflect at every point, right? The deflection of the compass tells us the direction of the magnetic field. But if I place it somewhere over here, there will be a neutral point. At the neutral point, if I keep a compass, it won't deflect in any direction, any specific direction. You rotate the needle, you keep it in some direction, it will be there. If you rotate and keep it in another direction, it will be there. It won't deflect in a specific direction. It won't orient in a specific direction. Why? Why does this happen? And doesn't it indicate that there is no magnetic field over there? So why isn't there a magnetic field at the neutral point? Because two magnetic fields cancel each other. Guess which are the magnetic fields? One magnetic field is due to the bar magnet, and another magnetic field is, yes, it is due to the Earth. So that is another proof that Earth produces magnetic field around its surface. Okay, so at the neutral point, the magnetic field due to the bar magnet and the magnetic field due to the Earth's surface or due to the Earth cancel each other. So I've given you three proof or evidence that Earth produces magnetic field. Number one, if you suspend a bar magnet, it will orient in certain direction. So that gives us a proof that there is a magnetic field produced by Earth. Number two, if you keep a magnetic material like iron buried inside the Earth's surface, it becomes magnetized due to the magnetic field produced by the Earth. And number three, if you keep a bar magnet, there will be a neutral point where magnetic field will be zero, and that gives us an evidence that the magnetic field due to the bar magnet was cancelled by the Earth's magnetic field. So these are the three evidences that magnetic field is produced by Earth. Okay, we have understood that there is a magnetic field produced by Earth and all. Done. But how does Earth produce this magnetic field? Or what is the source of this magnetic field? Or source of this magnetism? Actually, we have learned that electric current produces magnetic field. But this was not the thought process back in 1600 when William Gilbert gave us a theory. Okay, if you ask me what is the actual reason for the magnetism due to Earth, I would say I don't know. It's not because I don't know, it's because it is not found yet. But there are a lot of theories. One of them being, or the first of them being, by William Gilbert. He said that inside the Earth's core, there is a giant bar magnet. Come on, think of it. It would be very convenient guess because Earth produces magnetic field, so Earth behaves like a magnet. So he said that why not? There will be a magnet inside the Earth's core. Well, right now that theory has been discarded because we know that inside the core of the Earth, the temperature is very, very high. And we have also learned that ferromagnetic material loses its magnetic property or becomes a diamagnet when the temperature is increased very high. And here inside the core, the temperature is huge. You can say humongous, right? So there cannot be a proper giant magnet at the center of the Earth. So that theory is gone. But there are other theories. For example, all material is made of nucleus, and there are electrons revolving around the nucleus. Inside the nucleus we have protons and neutrons, and outside we have electrons. But protons and electrons are charged particles, and we know that Earth rotates about its axis. So if this is Earth and this, okay, I'll just show you. So this is Earth and this is the axis of rotation. So Earth will rotate about its axis. Yes or no? So all the material present inside the Earth, it is also rotating. So can we say that the charged particles are moving, and moving charged particles contribute to electric current? And we know that from the previous chapters, electric current produces magnetic field. So this is a theory. Keep it in mind. There is another theory that cosmic rays, they ionize the atmosphere. So in the atmosphere, ions are produced, and again the same scenario. This is the axis of rotation of Earth. Earth is rotating. The atmosphere surrounding the Earth is also rotating, and the atmosphere contains ions. So the ions are also rotating, and again ions are charged particles, and charged particles moving produce electric current, and electric current produces magnetic field. That is another theory. Another theory you want, okay, you have another theory is that if we know that inside the core of the Earth there is molten metal, and in molten metal also ions are present. Okay, so molten metal is actually, the ions are actually moving in this conducting liquid. So conducting liquid, in that ions are moving, and the Earth is revolving, Earth is rotating, and the ions are continuously moving. So it contributes to electric current, and again, yes, you guessed it right, it produces magnetic field. So these are the theories. Now if you ask me which is the correct theory, I don't know, but the last one seems to be most closest to the actual scenario, because when we compare the magnetic field of Earth, Moon, and other celestial bodies, maybe like Venus and Jupiter, then what we see is inside the Moon there is no molten lava or molten metal. And yes, it is not a coincidence that on Moon's surface there is no magnetic field also. magnetic needle will not deflect on Earth, on Moon. So is it a coincidence? I don't think so. Let's take the scenario of Venus. Venus, the rotation of the Venus is slower compared to the Earth's. And yes, you guessed it right, the magnetic field there also is weaker, because slower rotation means lesser current, and lesser current means what? Less magnetic field strength, right? And if you compare it with Jupiter also has molten lava, molten metal inside that. And the Jupiter rotates quicker than Earth, and the electric current there would be greater, and the greater electric current will contribute to greater magnetic field. Okay, so these are just conspiracies, oh sorry, not conspiracies, theories, uh, about how magnetic field is produced by these celestial bodies. And let's come back to Earth. So we have such theories. Now we know that magnetic field is produced. Now, to understand the magnetic field properly, we need to understand different definitions. So that's what we're going to learn first. First of all, what is geomagnetism? Yes, the branch of physics which deals with the study of magnetism on Earth. Okay, so you can see here the branch of physics which deals with the study of Earth's magnetic field is called geomagnetism, or there is another name for it. It is also called terrestrial magnetism. Okay, geomagnetism or terrestrial magnetism. So this is the branch of physics which deals with this. Now let's see how the magnetic field is actually. Yes, the magnetic field is something like this. You can see here the magnetic field lines go this way. So yes, we know that magnetic field lines originate from north and end at south, outside the bar magnet. So this is the North Pole, and from North Pole the magnetic field lines are going to the south, and then going back to the north, then going back to the south, and so on. So this is how the magnetic field lines are going. No wonder William Gilbert thought that there is a giant bar magnet like this, which is not the case. So this is just a representation. This is just a representation. As you can see here, there is no actual magnet inside the Earth, but the magnetic field lines produced by the Earth looks like there is a magnet there. And it has been calculated that the dipole moment of the magnet, if it was there, would be around 8 into 10 raised to 22 ampere meter square. And the magnetic field strength produced by the Earth is around 10 raised to minus 4 Tesla. Now 10 raised to minus 4 Tesla is another unit actually. It is 1 Gauss. So we can say the magnetic field strength of Earth is around 1 Gauss. Okay, that's clear then. Now let's go into other definitions and other nomenclature here. So you can see this is the axis about which Earth is rotating. So look carefully. This is the axis about which Earth is rotating. So you can see the rotation shown here. This is the rotation of Earth. So Earth is rotating about this axis, and I said earlier the magnetic needle, if it is allowed to, it is freely suspended, it will not orient in this direction. It will orient slightly, it will be slightly misaligned. It will orient somewhere like this, in this direction. So what is this? This is the direction of actual magnetic North Pole and magnetic South Pole. So here, one definition here is, this is the geographical North Pole, okay, and this is the geographical South Pole. Can you see that? Okay. Now, but magnetic South Pole is somewhere here. So you should not get confused by this nomenclature. You see here, this is geographical North Pole, but magnetic South Pole is somewhere here. Okay. If you see NCERT textbook, they have written that it is magnetic North Pole here, but the South Pole of the magnet, imaginary magnet, is here. So whichever way you want to say it, anyway, the South Pole of the magnet, imaginary magnet, is over here near the geographic North Pole, and the north pole of the imaginary magnet is near the, yes, geographic south pole. Is this clear? Now, other nomenclature. What is this line that joins the north pole and south pole? This is called the geographical north pole or the true north. So true north and true south, if I join it with a line, this line is called geographical axis or polar axis. It's the axis about which Earth rotates. But there is another axis here. What is this? This is the magnetic south pole and magnetic north pole. If I join them, yes, what would we get? We would get magnetic axis. So this is what is written here. Oh, it's not marked. Anyway, this is magnetic axis. This is magnetic axis. Now, two more definitions here: geographical equator and magnetic equator. What are they? Okay, suppose you take geographical axis, okay, and you take a plane. Okay, I'll show here. Suppose this was geographical axis and there is a plane perpendicular to the geographic axis. So there is a plane perpendicular to the geographic axis. Now this plane will cut Earth into two pieces, and the way it has cut, the area or the cross-sectional area that you would get is a circle. So that circle is geographical equator, and this plane which cuts the Earth is called geographical equatorial plane. Geographical equatorial plane. So I'll repeat, geographical equatorial plane is a plane perpendicular to the geographic axis, okay, and the cross section that it cuts on the Earth is geographical equator. Clear? Now please think over it. What would be magnetic equator? I'll give you a time. Give you some time. What will be magnetic equator? Yes, you guessed it right. Instead of geographic axis, if you have magnetic axis, so here you can see the magnetic axis is slightly tilted. So if you have magnetic axis and perpendicular to the magnetic axis, you have, yes, the magnetic equatorial plane, and the plane cuts the Earth into two halves, and this circular cross section that you get is magnetic equator. Okay, and this Earth, there is only one Earth. So Earth has been cut into two pieces, I told. So the two pieces, out of the two pieces, the piece which contains the true north, geographical north, is called the northern hemisphere, and the hemisphere which is half of a sphere. We know that Earth is a sphere, right? So the half of the sphere or the hemisphere above this equatorial, above this magnetic equator, in which the geographic north is present, is called is called the northern hemisphere, and the hemisphere which contains the geographical south is called southern hemisphere. I hope it is clear. Now all these definitions are there. I forgot to mention in the beginning, do not waste time writing the notes. You can concentrate in the class, listen properly. I forgot to tell you this in the beginning. I should have told you this in the beginning. So no need to because people can't concentrate on two things at a time. So if you're either listening or you're either writing. So if you waste time or if you spend time on writing, then you won't be able to concentrate on listening part. So I would suggest that all of you listen properly, and the notes, then who will give you the notes? I will give you the notes, because already in the presentation everything has been written. The notes are properly written, and apart from this, if anything else is required, I'll be providing you with that. Okay, so I hope this slide is clear. All the explanations are clear. Let's proceed. Yes, what all I told has been written here. Geographic axis, it is a straight line passing through the geographical poles of the Earth, the geographical north pole and south pole. It is also called the axis of rotation or the polar axis of the Earth. Okay, the figure here is nothing but the figure that you saw earlier. Now let's proceed. Let's proceed to the next slide. Now, geographic meridian. This was not mentioned in the previous slides. What is geographic meridian? Geographic meridian is a vertical plane. As you can see here, there are two planes. One of them is geographic meridian. In this figure, this plane that you see, this one is the geographic meridian. But what is the speciality about this meridian or this plane? It's any vertical plane? No, it is a vertical plane which contains the point where we are right now and the geographic axis. So geographic axis is a line. If this line is contained in a plane, that plane can be any plane, it can be oriented in any direction. But how do you fix this plane? There is one more condition, the point or the place where we are at right now. So this place and the geographic axis, if it is placed in a single vertical plane, it is called geographic meridian. So you can see here, geographic meridian, it is a vertical plane at any place passing through the geographical axis of the earth. So geographic axis, the place where we are right now, and if you merge them together in a vertical plane, that is geographic meridian. So that's what you can see here. This plane is geographic meridian. Now what is this mm? It's not millimeter. It is magnetic meridian, which we'll see in the next slide. Okay, so GM stands for geographic meridian and MM stands for magnetic meridian. Now use your common sense. If geographic meridian is a plane passing through the geographic axis or the axis of rotation, what would be the magnetic meridian? Oh, okay, magnetic meridian is in a different slide. We'll come to that. Okay, we'll come to that one by one. So let's go to geographic equator. We have already discussed this. So let's rush through this. Geographic equator, it is the great circle on the surface of the earth in a plane perpendicular to the geographic axis. We have already discussed this. All the points on the geographic equator are at equal distance from the geographic poles, which is clear. If this is the geographic pole, the distance to this point, all are equal. This is the geographic equator. Let me use a pen to make you understand that. Yeah, this is the pen. So you see, distance from this point of the equator and this point of the equator. See, these distances will be same, and that goes for all these lines. All these lines, the distances will be same. That's what is mentioned here. All the points on the geographic equator are at equal distance from the geographic poles. I hope it is clear. And this is a video recording. Obviously, if you were online, I would clearly ask you whether you have understood all these things, and accordingly, if you have not understood something, I would repeat that. Okay, so let's proceed to the next slide. What is so continuation of geographic equator. A great plane which passes through the geographic equator and perpendicular to the geographic axis is called geographic equatorial plane. This plane that we were talking about earlier. Okay, now this plane cuts the earth into two equal parts. Okay, so yes, the geographic equator cuts the earth into two equal parts. One is northern hemisphere and the other one is southern hemisphere. So yes, we can read this. Let's proceed to the next part. Magnetic axis, we have already discussed this. It is a straight line passing through what? Magnetic poles of the earth, and it is inclined to the geographic axis. Yes, this angle, it is almost 11.5. What is that angle? This angle. They are talking about this angle over here. This angle is approximately 11.5 degrees. But mind you, it is not constant. The magnetic field produced by earth is complex, it is complicated, it is weird. So because of that, it continuously changes. This angle continuously changes. It's not a constant value. Remember that. Okay. So yes, good luck with that, Wilbert, because Mr. Wilbert had suggested that there is a single permanent magnet. So what would be actually happening is that magnet is orienting in different directions at different time. So that is not what is happening. So by William Gilbert. Now let's continue. 11.5 is almost the angle made by the magnetic axis with the geographic axis, and that is what is shown here. It's a bit hard to write on the screen. I'm using a laptop for this purpose, and if I had been using a tablet, it would have been easier. Next time I will use a tablet. Now let's continue. Yes, magnetic meridian. So yes, earlier we had seen this plane GM, which stands for geographic meridian. So this plane is actually magnetic meridian. So what is magnetic meridian? We had already seen it's a vertical plane at any place passing through the magnetic axis of the earth. It is a vertical plane at any place passing through the axis of freely suspended bar magnet. That's another very important definition that you can see. So that means if I have a bar magnet and I'm suspending it, it won't orient in any random direction. It will orient along the magnetic meridian. So suppose this is geographic meridian and I am keeping the bar magnet like this. Will it stay there? No, it will orient somewhere like this. So this is magnetic meridian. So magnetic meridian is a vertical plane passing through not only the magnetic axis, it is also passing through the axis of the freely suspended bar magnet. So you have a freely suspended bar magnet. The vertical plane passing through this freely suspended bar magnet is also magnetic meridian. Got it? So let's continue. So it is a vertical plane at any place passing through the axis of freely suspended bar magnet or magnetic needle, and it is also the vertical plane at any place which contains all the magnetic field lines of the earth at that point. So that means, let's go back to the slide where I showed you the magnetic field lines, which was in the beginning somewhere. Yes, here. So let me move my my video. So yes, you can see the magnetic field here. So at any point, which point should I take? Let's take this point. So this line will be on the magnetic meridian. So the plane, this vertical plane, which I can take like this vertical plane will be magnetic meridian. It's a bit hard to visualize, but we will see other pictures. I promise you that even if you didn't know anything of the previous chapters, you will clearly understand everything in this chapter from this video. So if I take a line here, this will be in magnetic meridian. Okay, so let's continue. Where were we? Yeah, magnetic equator. Yes, so magnetic equator. Again, magnetic equator, it's a very simple thing. It is a great circle on the surface of the earth in a plane perpendicular to the magnetic axis. All the points of the magnetic equator are at the equal distance from magnetic poles. Yes, this is the magnetic pole. So all the points on the magnetic equator will be at the same distance from magnetic poles. It's clear. Okay, so let's continue. Now we are actually talking about the three elements which are required to completely understand the magnetic field. We learned that magnetic field is there. Earth produces magnetic field. That's what we have learned till now. Then we have learned different terminologies, and now we are actually going to learn what are the three different things or three different entities you need to measure in order to find the magnetic field. But see, clearly magnetic field is a vector, so we need its magnitude and also its direction. So you need to specify the direction. So to specify the direction, you need two angles. Okay, so one angle is enough, right? No, but see, what we are doing is, let's say there is a magnetic needle or a bar magnet. It will orient somewhere in the horizontal plane. This is the horizontal plane. So in the horizontal plane, it will incline in some direction. So this angle you need to know. And apart from that, the magnetic needle will not be suspended like this. It's in your compass. Your compass does not allow it to rotate in the vertical plane. So there is another device called dip circle. We will learn it in coming slides. So in dip circle, you will understand that magnetic needle, it also orients in the vertical plane. So that's what is shown here. So here, if this is the geographic meridian, or this is actually the vertical projection. I'll just show you with the laser, okay, so that the figure does not get distorted. So this is the projection of the geographic meridian, and this is the projection of the magnetic meridian. So what is this D? This D is angle of declination, and it is the angle between what? Guessed it right. Geographic meridian and magnetic meridian. So angle of declination is the angle made by the geographic meridian and the magnetic meridian. So I'll have to take two books now. Okay, so let's say this one is geographic meridian, and let's say this one is magnetic meridian. So this angle between them is nothing but, come on, angle of declination. So you will see in the you might have seen here in this figure, what is this phi? This phi that you see, I did not talk about this phi earlier because I wanted to talk about it that after I had discussed angle of declination. So this is nothing but angle of declination. Now tell me one thing. You have heard about that 11.5 degrees earlier. 11.5 degree which we talked about was the angle made by which two entities? It was the angle made by the magnetic axis and the geographic axis. So is angle of declination the same as that? Think about it. No. This, I don't know, some students find it difficult to understand this concept. So I have some figures with me in the coming slides which will clearly make you understand that angle of declination is not equal to the angle made by geographic axis and the magnetic axis. Remember that. It is the angle made by the geographic meridian and the magnetic meridian. Okay. Well, before I show you the figure, let me try to explain that using two lines. So let's say these two. Now this angle made by these two markers can be said as the 11.5 degree that we saw earlier. This is the angle between magnetic axis and the geographic axis. Now if I orient this, tell me, now does the angle seem same? The angle has changed. Suppose if I orient like this, now is the angle same? It's almost zero now. So you see, it depends on where you are looking from. So we learned that geographic meridian and the magnetic meridian is actually vertical plane which contains the plane which contains the place at which we are present. So the orientation in which you are looking the geographic axis and the magnetic axis, it will differ place to place. Okay. So earlier that 11.5 was actually if you are keeping both geographic axis and the magnetic axis in a single plane. If you keep it in a single plane, the angle is 11.5. But the angle made by the geographic meridian and the magnetic meridian will not be same. I'll show you the figure in coming slides. We have already learned about this geographic angle of declination. We have already discussed. Anyway, I'll just read it. Angle of declination at a given place, the acute angle. Oh, that's another thing. We could have also measured this angle. Sorry. We could have also measured. Oh, sorry. We are in this plane. So let me take the pen. So we could have also measured this angle, right? But this would have been obtuse angle. So the definition is clear. It should be the acute angle between the magnetic meridian and the geographic meridian. Is that clear, everyone? Now, there is another figure of inclination. We will talk about this later because that will come later. Actually, we were in this slide. Sorry. So here, this angle is not angle of declination. This acute angle is the angle of declination. I hope it is clear. So yes, at any given place, the acute angle between geographic meridian and the magnetic meridian is called angle of magnetic declination, or simply declination. It is represented by D, or in this case we have used phi also in the previous slides. So phi is what we use in this slide, but angle of declination can be represented by capital D also. That is the standard representation. So yes, it is the angle of declination or declination at a given place. It is the angle between the geographic north-south direction and the direction indicated by the magnetic compass. Okay, so magnetic compass is showing some direction. So this is the magnetic compass or the magnetic needle. So the angle is D. Now this angle is taken as positive because it is towards the east. We'll see in the next slide. So yes, you can see it here. This is the positive magnetic declination. Sorry. Yeah. So this is the positive magnetic declination and this is the negative magnetic declination. And we know that this is C, north, south, and this is east, west. So if the compass is rotating, in this case clockwise, that is towards east, then this is positive declination. And if it is rotating in the other way, towards west, then it will be negative magnetic declination. Is that clear, everyone? Now let's proceed. This is the figure I was talking about, which will clearly make you understand that angle of declination is not equal to the angle made by the magnetic axis and the geographic axis. That was 11.5 degrees. That's not this, and it depends on the place, and from place to place it will vary. You can see here in this figure. So this is the direction. See, this is the north pole, true north or geographic north. So this line or this plane is the plane in which it is the plane of geographic meridian. Okay, this plane contains geographic meridian, and you see the magnetic north is somewhere here. Can you see that? Magnetic north is somewhere here. Yes. So this line which joins this place, oh, we were talking about this place, sorry. So from this place, this line is magnetic meridian. So this angle is angle of declination. This angle is angle of declination. So you see it varies from place to place. At this place, this is the geographic meridian and the magnetic meridian is along this. So the angle is very small over there. The angle of declination is very small. And again here, this point you see, the geographic meridian is along this. Magnetic meridian is also along this. So what is the angle of declination at that point? It is 0. You get it? The angle of declination is 0 at that point. Clear? Let's proceed. Okay, so that's it. And again, this is positive declination, this is negative declination, which we have already mentioned in these two figures. So it's all clear. So angle of declination is clear. So this is one angle by which we will represent the magnetic field, the resultant magnetic field, or the actual magnetic field produced by Earth. We will be representing with this angle, which is angle of declination, and another angle, which is angle of inclination, which is shown here, or which we will see in the next slide. So this is angle of dip or angle of inclination. What is this? It is the angle made by the magnetic needle from the horizontal. So which plane is it rotating in? Yes, it is rotating in the vertical plane. This is the vertical plane, right? So if the magnetic needle, this was like this, if it rotates in the vertical plane about a horizontal axis, this angle made by the horizontal, this angle made by the horizontal and the magnetic needle is called angle of dip or angle of inclination. Yes, that's what we see here, angle of dip or inclination. It is an angle which in which the direction of resultant magnitude of the Earth's substance with the horizontal line in the magnetic meridian. So horizontal line in the magnetic meridian, and this is the resultant magnetic field. So resultant magnetic field and the horizontal will make an angle of dip or angle of inclination. Is it clear to everyone? Let's proceed, and it varies from place to place. I will show you another figure, just like I showed you that angle of angle of declination varies from place to place. I will show you that angle of inclination or angle of dip also varies from place to place. So it is an angle which the axis of freely suspended magnetic needle up or down. It depends on which hemisphere we are in. Okay, it subtends with horizontal line in a magnetic meridian at a given place. Okay. Yes. Now this is what I was talking about. In northern hemisphere, you think about it. Northern hemisphere geographic north is there, but just beside that, which pole of the imaginary magnet inside the Earth is present? South pole. You know why this naming, why this confusion in the naming happened? Because initially, when a magnet oriented almost in the north-south direction, they understood that there are two poles of the magnet, so they had to name the two poles of the magnet. So this brilliant people, it's just a mistake that they named it in this way. That is, the pole which was pointing towards the north was named as north seeking pole, meaning north, the pole which is seeking north or pointing towards north. But nowadays we know that which pole points towards north? The south pole, right? But they named it north seeking pole. Okay, north seeking pole was okay, it's correct, it is seeking north, it is pointing towards north, so it is north seeking pole, it was all well and good. But later on they just made it short. North seeking pole was named as north pole. Just like mobile phones, mobile phone was the name, but now we call it mobile, right? We just call it mobile, but it's actually a wrong way of saying it, because mobile means what in English? Mobile means anything that we can move. Right? So according to me, ball is mobile, so book is mobile, ball is mobile, marker is mobile, everything is mobile, but we call this a mobile. I hope it is understood. So yes, that same thing happened there. North seeking pole became north pole, so north pole is pointing towards north pole. So that means north and north attract? No. So actually, the north pole of this suspended magnet is pointing towards geographic north, but in actual scenario, what is present over there? Magnetic south pole of the Earth is present over there. Okay. So I hope that is clear. Now let's come back to the topic. So angle of declination, angle of dip. So we see that what is angle of dip? It is the angle made by the magnetic needle with what? The horizontal. So now if you're going towards the northern hemisphere, what is present there? North pole of the Earth, but magnetic south pole is present over there. So guess which pole will be pointing downward of the magnetic needle? If this is south and this is north, or this is south and this is north, which will be that? The south pole of the Earth's magnet is present in the geographic north, which is present in the northern hemisphere. So magnetic needle will be orienting in such a way that the south pole or the north pole, which one is that? North pole of the magnetic needle will be pointing downwards. Why? Because the Earth's magnet's south pole is present over there. So south and north attract. So magnetic needle's north pole will be attracted to the south pole of the Earth's magnet. Clear? So yes, that's what is written here. In the northern hemisphere, north pole of the freely suspended magnetic needle will dip downwards. Understood? And that is towards the Earth's surface. So in southern hemisphere, what will happen? Now, how to remember this? You don't have to go with the logic. Now, north pole, geographic north pole, magnet south pole, then suspended magnets north pole. Oh my God, it's so weird. No need to remember it like that. Northern hemisphere N. So north pole will be pointing towards the Earth. That's how you remember it. So in southern hemisphere, which will be pointing towards the Earth? South pole. That's what is shown here. South pole of the freely suspended magnetic needle will dip downwards, that is towards the Earth's surface. Is that clear, everyone? Okay. So I hope I'm not going too fast. Yeah, I will, clearly, adjust my speed according to the audience. So if the audience the students feel that I'm going a bit too fast, because everyone's mind doesn't work the same way. Some people, everyone understand things, okay, but it depends on the speed with which you understand things differ from people to people. So I suggest, I don't want any radio mode of teaching. I have devised two modes of teaching. One is radio mode, and another one is telephonic mode. Now radio mode, what is that? Radio mode, in a radio, when you listen to a radio, only radio will talk. You won't talk back. Will you talk back to a radio? If you talk back, then people will call you some name. I'm just saying. But in a telephonic mode, what happens is, see, you talk back to the telephone. No one will call you mad if you talk back to a telephone. If you don't talk back, then they might call you mad. Why are you wasting the money? You're just listening to the other person. Yeah, well, if it is a conversation between a husband and a wife, and if they are cross with each other, then usually it is a one-way traffic from wife to husband. I'm just saying, okay. So in other scenarios, we usually talk back to the telephone, right? So in telephonic mode of teaching, both ways communication should be there. That means I will be teaching, but that doesn't mean only I will be speaking. You should also speak, but don't. It should not be at the same time. In telephone, if the other person talks at the same time you are speaking, will anyone understand anything? Not at all. You should speak when the other person is not speaking, and the other person should speak when you are not speaking. Is that clear? So I want that kind of teaching. So you give me a feedback, you make me understand whether this speed is okay for you, or should I go faster, or should I go slower? Okay. Ultimately, the aim is to complete the portion and also to make you understand things. Okay. And obviously, ultimately, you have to score good marks in the board exams. Is it clear? Not only the board exam, don't stop there. You have to score good marks in the competitive exams like JEE, JEE Mains, NEET, and JEE Advanced as well. So I hope you're ready for that. And if you give me enough opportunities, and if you listen carefully in my classes, and I will make you crack these wild wild the exams that you consider very difficult. Okay, so let's continue. Let's not get sidetracked. So this is about northern hemisphere and the southern hemisphere, and we are talking about the dip, angle of dip, downwards, upwards, everything. Clear? Now this is the figure I was talking about, where you can understand. Okay, this figure we have already seen. This figure we have already seen. Now I'll just move it somewhere here. Okay. So I'll take a laser. Okay. See here. So this is the magnetic field line. Can you see this? This is the magnetic field line. So this is the imaginary magnet. This is the imaginary magnet inside the Earth's surface. So this is the magnetic field line. So can anyone tell me whether the line, the magnetic field lines will be outward or inward? Okay, this is not the it's weird. They have shown the magnetic field lines going into the North Pole. It's actually wrong. Okay, magnetic field lines. Oh, sorry. So magnetic field lines will be actually originating from the North Pole and going into the South Pole. Or they have actually represented it. Sorry, I did not see this figure. So you see the geographic North Pole is here. So magnetic pole is over here. So this is actually the figure of the imaginary magnet they have shown, but this should be South Pole and this should be North Pole. There is a mistake in this. So yes, the magnetic South Pole will be near the geographic North Pole, and that's why the magnetic field lines are going into the South Pole and coming out of the North Pole. Okay, anyway, now let's talk about this point. This point on the Earth's surface, this is the dip circle. I will talk about the dip circle in coming slides, but you can understand it as the magnetic needle, just a magnetic needle over there. So this is a magnetic needle. It is allowed to rotate in the vertical axis, vertical plane. So this is the vertical plane. So in the vertical plane, if it is orienting in this direction, so what does that mean? This angle is the angle of dip. That angle is the angle of dip. Let's take here. This is the vertical plane now. This is the vertical plane. By the way, what is this? What is the name of this vertical plane? Yes, it's magnetic meridian. Magnetic meridian. So magnetic meridian or in magnetic meridian, this needle is orienting in this direction. Okay, so what is the angle of dip here? This is the angle of dip. So you can see from the figure, angle of dip is greater here and it will be less here. I told you the figure is not neat because it's a bit hard to draw on the surface of the laptop screen. Anyway, now if you see, as you go this way towards the equator, the dip angle is decreasing. Can you see here what is the angle of dip? This is the vertical plane. Okay, so angle of dip does not make any, this is a horizontal line. Okay, it's a vertical line. No, you consider yourself to be standing over here. So you are standing like this. You are standing like this. This is your head, this is your hand. Oh my god. So this is your hand. A wonderful figure. Yes, that's your head. So this is you, and to you this is horizontal. This will be horizontal. So you see the magnetic needle does not make any angle with the horizontal. So yes, what is the angle of dip at the equator? A big 0. And what is the so guess what will be the angle of dip at the north pole and the south pole? So at the pole, can you see this? At the pole, the magnetic needle is actually oriented like this, vertically. So what will be the angle of dip? Come on, the angle made by the magnetic needle with the horizontal, it will be 90 degrees. That's what you see here. Okay, now again, you can see here this figure. This figure shows this is the thread with which you are suspending the magnet, and this is the magnet, and magnet makes an angle of theta with the horizontal, and this is nothing but angle of dip. It's all clear. Now again, this figure shows another magnet. Now you see this is the direction of actual magnetic field line. So here you see, I'll just clear the screen so that you can see it. So this is the real or actual or complete or total magnetic field, resultant magnetic field of Earth. So that will be this. So this will be the resultant magnetic field of Earth. Resultant magnetic field of Earth is denoted by B, and this is angle of dip. So can you use the vector, the components of vector that you have learned in a previous year to find the horizontal component of the magnetic field? If this is magnetic field of Earth and this is angle made by the horizontal with the resultant magnetic field, so if I drop a perpendicular, this will be horizontal component, and the horizontal component is denoted by B with a subscript H. And if you say this is the vertical component, this will be the vertical component, and it will be denoted by B with a subscript V. Is this clear? Okay, we will see other slides also, so don't worry, everything will be clear. So yes, so the magnet points, again magnet points in the direction of the actual magnetic field. So it makes an angle of theta with the horizontal, which is angle of declination, angle of inclination or angle of dip. So the component of the original magnetic field with the horizontal, which is called the horizontal component of the magnetic field of Earth, and is represented by BH, will be B cos theta. We will see it in other slides also. So here also you can see this is the point. The magnet is oriented in this direction. The magnetic needle is oriented in this direction, which clearly says that is the direction of magnetic field produced by the Earth. And this is the angle of inclination, yes, I, and horizontal component is shown here, and the vertical component is shown here. Many figures, same concept. Clear? Again, you can see the maximum angle of dip is near the north pole or the south pole, and minimum dip is at the equator. Okay, mind you, it's not the geographic equator, it's the magnetic equator. Is that clear, everyone? Let's go. This is almost the end of the chapter, end of the topic. Now we are going to learn about the measuring device, which is called the dip circle. Okay, dip circle, it is the measuring device. It is the device with which you will measure. So I'll show you different figures of the measuring device. Let me wait 1 second. Yes, so here you can see One second. Yes, this is one. I'll use a laser. Huh. So this is one figure of the device. This is another view of the device. So here you can see there are two graduations, this one and this one. Can you see that? So this graduation, this one, will show you the angle of dip at that in that plane. So this graduation shows you the angle made by that this vertical plane. So this is the vertical plane. Vertical plane, in that vertical plane the angle of dip is measured. So how is that vertical plane oriented? Is it along the magnetic meridian, or is it slightly inclined from the magnetic meridian? So that will be decided by the angle shown here at the bottom. Okay, so once you have fixed that, now you can measure the angle of dip in this graduation, and this angle is the angle of dip. This angle is the angle of dip. Is it clear, everyone? And this will be the direction of actual magnetic field of Earth. Now let me move this figure, sorry, move my video. Now you can read here. One second. So dip circle, angle of dip at any at a plane is measured by the instrument called dip circle. More figures will be there in the next slide. Okay, and dip circle, it gives you angle of dip. Now there are two kinds of angle of dip. Actually, there is one kind of angle of dip, the angle of dip that's there in the magnetic meridian, which is the angle of dip, or it's also called true dip. Now apparent dip is there if the dip circle, the vertical plane of the dip circle, is not aligned with the magnetic meridian. Instead, if it is aligned with another plane, oh, that will be geographic meridian. Not necessary. It can be any plane, any vertical plane. If the dip circle is oriented along any vertical plane other than the magnetic meridian, then the angle of dip shown by that will be apparent dip. It is not the true one. It is apparent. Apparently, it will be different. So yes, angle of apparent dip will be different from angle of true dip. We will see that. We will see the relations between them in the coming slides. Okay, so let's continue. This is the dip circle in which a magnetic needle is free to rotate in a vertical plane about its horizontal axis. So yes, if there is a vertical plane and the magnetic needle is allowed to rotate in a vertical plane about the horizontal axis. Okay? So ends of the needle move over a vertical scale graduated in degrees. So this is the end of the needle. It will move over a vertical graduation shown there, and it will measure the angle of dip. So these are other figures, some old figures of angle of dip circle. So these are dip circles, dip circle, dip circle, dip circle. So you see all these dip circle have this horizontal graduation as well as vertical graduation. Sorry for that. So that's that. Okay. So now let's proceed to other components. Now we told that three elements are required to completely understand the magnetic field. One of them was angle of declination, which was the angle made by the magnetic meridian with the geographic meridian. And second one was angle of dip or angle of inclination, which was the angle made by the magnetic needle with the horizontal. And now the third thing you need to know is horizontal component of Earth's magnetic field. So magnetic field, the magnet is oriented like this. So this is the actual magnetic field, but the component of the magnetic field along the horizontal will be horizontal component of Earth's magnetic field. That's what is shown here. So horizontal components of Earth's magnetic field. So yes, this phi is the angle of declination. This theta is the angle of inclination or angle of dip, and this is the actual magnetic field. So this component, this BH, is the horizontal component along the magnetic meridian. This plane is the magnetic meridian, and the plane which is shown on the other side is the geographic meridian. Is that clear? Okay. And the magnetic field is shown downwards. Clearly it is because it is the northern hemisphere We told that the north pole will be oriented downwards, and the magnetic field line will be along the direction in which the north pole is oriented. So yes, all these things are clear. This is the vertical component, this is the horizontal component, everything is clear. Now the horizontal component of Earth's surface, Earth's magnetic field at a given place is the component of the resultant magnetic field of the Earth along the horizontal line in a magnetic meridian. Okay, so that's the component along the horizontal direction. We have discussed that. That's what is written over there. Now let's proceed to the equations. So we clearly have discussed that the cos component is horizontal component and the vertical component is b sine theta. Now if I take the ratio of these two things, b sine theta divided by b cos theta will give me tan theta, because b will get cancelled, and in the numerator it will be bv and in the denominator it will be bh. I'll repeat, b sine theta divided by b cos theta will become tan theta, and on the right hand, on the other side, you'll get bv divided by bh. So clearly bv divided by bh is tan theta. You can get it from this figure also. So you see, this is the vertical component, so you can show it here also. This is vertical component. So tan theta, tan of this angle, is opposite divided by adjacent. So opposite is bv, the vertical component of Earth's magnetic field, and this is the adjacent side, which is the horizontal component of the magnetic field. So tan theta is equal to opposite by adjacent. Very much clear. And yes, if you know the horizontal component and the vertical component, you can find the resultant by this equation, which you already know. This is a very simple topic. The true dip, apparent dip, all these are very simple. Okay, so you know the horizontal component, you know the vertical component. These are two vectors which are perpendicular to each other. When you have two vectors perpendicular to each other, the resultant will be root of a square plus b square. That's all. If it was inclined at an angle theta, then you have a greater equation, which is resultant is equal to, the magnitude of resultant obviously, is equal to root of a square plus b square plus 2ab cos theta, where theta is the angle between the two vectors. So you see, if the angle theta is 90 degree, you substitute 90 in that cos theta, cos 90 will become 0, that term will vanish, so only this will be left. The resultant will be root of bh square plus bv square. Now that's that. At magnetic poles, okay, now at magnetic poles we have already seen that the magnet will be oriented in the vertical direction, so theta will be 90. Another reason is the horizontal component is 0 there. Okay, only vertical component is there. Again, at the equator it is oriented horizontally, so there is no vertical component, so vertical component will be 0. So this ratio, what will happen? This ratio will become 0 or theta will become 0. All these things are already discussed in the previous slides. Let's proceed. Now apparent dip. Apparent dip. Now this is the main crux of this topic. Here, this is the magnetic meridian. This plane is the magnetic meridian. What is the plane shown behind that? Is it geographic meridian? Not necessarily. It can be any vertical plane. So any vertical plane which is inclined at an angle of alpha with the magnetic meridian is shown over there. So what you want to find is the angle of dip along that direction. Meaning the dip circle, the vertical plane of the dip circle, is now not oriented in the magnetic meridian, but it is oriented along the other plane that is shown over there. So if the dip circle is oriented along the other plane, then what will happen? The inclination shown will not be same as the actual inclination. So now that will be a difficult thing. So how will we know whether we are actually oriented in the magnetic meridian or some other plane? Now, so whatever dip is shown by the dip circle, is it the true one or the apparent one? How would we know? I will tell you. So first of all, what is apparent dip? It is the angle of inclination or angle of dip in a plane which is not magnetic meridian. That's all. Any other plane whatsoever. It can be geographic meridian also, but not necessarily geographic meridian. It can be any plane. Okay. So let's continue here. Apparent angle of dip, which is represented by I dash or theta dash. So when the plane of vertical scale of dip circle is in the magnetic meridian, the needle rests in the direction of Earth's magnetic field. Okay, when the plane of vertical is in the magnetic meridian, we we know that the needle will rest in the direction of resultant or actual magnetic field of Earth. But okay, the angle made by the needle is called the true dip. That's already discussed, or actual dip. But if the plane of vertical scale of dip circle is not kept in the magnetic meridian, then the needle will not indicate the correct direction of the Earth's magnetic field. So that will be a faulty value. The angle shown there will be faulty. The direction shown there will be faulty. Okay. In this situation, the angle made by the needle with the horizontal is called apparent angle of dip. So that's apparent angle of dip. That means if we are talking about this plane, sorry, I'll just move this video. So this plane, if I show that plane somewhere here, I'll show that plane here. Okay, so that means this is the horizontal component in that plane. So is it the actual horizontal component? No, it will be some apparent horizontal component. How do you get that? Because this is the actual horizontal component and you have a component of the horizontal component. Now don't get confused. Horizontal component in the magnetic meridian is the horizontal component of the actual resultant of magnetic field or actual magnetic field along the horizontal line. Now you are inclining the plane with some other in some other direction. So what will you have? You will have the component of horizontal component in the magnetic meridian. That means this BH, you will have a component of BH along this. So this will be 90 degree. So I'll just show that first. So suppose this is BH and this is the other plane. This is a new plane that we have taken, which is not along the magnetic meridian. So this component BH dash, this angle is alpha. Okay, so what will be the component BH dash? BH dash will be equal to BH into cos alpha. It's a bit hard writing here. So BH into cos alpha will give you BH dash, which is the component of horizontal or which is the horizontal component along another plane. But what happens to the vertical plane? Vertical component will remain the same. Why? Because this edge is common to both. This edge is common to both the planes. So the vertical component will be same. Horizontal component will be different because the horizontal edge or the horizontal line is now inclined. It's not the same. I hope it is clear. So yes, in this situation, the angle made by the needle with the horizontal is called the apparent angle of dip. So suppose the dip circle is set at an angle alpha to the magnetic meridian. The effective horizontal components. So effective horizontal component, which is the component of horizontal component in the magnetic meridian, will be BH cos alpha, and no effect on the vertical component will be there. So we have already seen that. Let's proceed. So let's complete this quickly. It's already stretched too far. So I'll keep my video here. So yes. So that's what we discussed. So now again, if we talk about that plane, this is the last slide. If we talk about that plane, this is the plane which is not the magnetic meridian, but on which we have found the apparent dip. So now BH dash will be somewhere here, and BV dash, which is equal to BV, because the vertical magnetic field component has not changed. So that will be BV dash or BV, same thing. So this line will show the angle of dip. Now this is angle of dip, but is it the true angle of dip? No, it is apparent angle of dip. Now again, if you take the tan of that angle will be vertical by horizontal, which is nothing but actually it will be opposite by adjacent, which will be nothing but vertical by horizontal. So tan theta dash will give you BV dash divided by BH dash, and which will be nothing but BV dash is nothing but BV. It has not changed. We told it earlier in the previous slide. And again, what is BH dash? We can see it is BH cos alpha. So in place of BH dash, I will write BH cos alpha. Is it clear? So we have already learned that BV divided by BH is tan theta. I'll clear that. I'll clear that and make you understand clearly. So yes, BV divided by BH is tan theta, which we have seen in which slide? Maybe somewhere here. Yes, here we have seen that tan theta is equal to BV divided by BH, and you can substitute that there. So if I substitute that there, I'll get tan theta dash, which is on the left hand side, is equal to tan theta in the numerator divided by cos alpha. So this is a very important relation which relates the apparent dip with the true dip and the angle between the planes, angle between the magnetic meridian and the random plane we have chosen. Now for a vertical plane other than the magnetic meridian, we can clearly see if the plane is magnetic meridian, alpha will be 0. If plane is other than the magnetic meridian, there will be some positive alpha. And when you increase the value of alpha, cos alpha will decrease, because the graph is like this, right? How is the graph of cos alpha or cos theta? This is the maximum, and then it will decrease, and then it will go to the negative side, and so on. So this is the graph. So yes, the cos alpha is decreasing. This is cos theta and this is theta. So cos value is decreasing. So when cos value decreases, here you see this is the denominator. When the denominator decreases, the value increases. Clearly we can understand 1 by 2 or 1 by 4, which is greater? 1 by 2 is greater because it is 0.5. 1 by 4 is 0.25. But whose denominator is greater? 4. 1 by 4's denominator is greater. So when denominator increases, the value decreases. So that's what we see here. Cos alpha. Okay, so sorry, the denominator is increasing here. I just made a mistake, sorry. Yeah, in this case, what is happening? Yes, the cos alpha value is decreasing. We saw from the graph, it's decreasing. So what will happen? The value will increase. The denominator decreases, so the value increases. 1 by 2 is greater than 1 by 4 because the denominator decreased. So yes, if tan theta value is increasing, that means theta value is also increasing. So theta dash will be greater than theta. So always apparent angle of dip will be greater than true angle of the true dip. So if two values are given, you have to identify which is apparent angle of dip and which is a true angle of dip. Which is greater, that is apparent angle of dip. You got it? So whichever is greater among the two, that will be apparent angle of dip. Okay, so that's what is written. So apparent angle of dip is always greater than or more than the actual angle of dip at any plane. Okay, for a vertical plane perpendicular to the magnetic meridian, alpha will be 0. Alpha will be 90. Now understand this. This is magnetic meridian. Let's bring back those books we had. So this is our magnetic meridian. Now if I have a plane which is perpendicular, sorry about that. So if we have a magnetic meridian, this is magnetic meridian, and if I keep a plane here perpendicular to it, so I'll show it here. So magnetic meridian and this plane is perpendicular to each other. Okay, I can show it like this, but you will not be able to see the angle. That's why I'm showing it like this. So this angle is 90. The alpha is 90. If I substitute that in this equation, then what do we get? Cos alpha, cos 90 will become 0. So tan theta dash will become infinity. And when tan theta dash is infinity, theta dash is, come on, it will be 90. So that's what is shown here. So theta dash will be 90 in a plane perpendicular to the magnetic meridian. Yeah. So earlier I asked you a question. So dip circle, it's oriented in some random way. So how will you understand whether the angle that it is showing is apparent angle of dip or true angle of dip? How do you know that? So how do you measure the true angle of dip is like this. Initially, the dip circle will be rotated in such a way that you get the angle of dip as 90. That means the magnetic needle points vertically in that plane. So you need to rotate the dip circle in such a way that finally you get the plane in which magnetic meridian is vertical. Is that clear? So magnetic meridian is vertical. That means this plane is perpendicular to the magnetic meridian. So I'll show you in this figure. Let's go back to the figure of angle of dip. Yes. Which one? This. Okay, this shows better. So here I'll erase the ink. Huh. So what we'll do is we will rotate in such a way that we'll rotate this vertical circle in such a way that this magnetic needle will not be oriented like this, it will be oriented like this. So this plane is actually perpendicular to the magnetic meridian. So you find this plane, you mark the angle, then just rotate 90 degree. Understood? So that's how you find magnetic meridian. Now you orient it in the magnetic meridian, the needle will be oriented somewhere like this. So what is this angle? This angle will be, or this angle will be angle of dip. Is it true or apparent? It is true. True angle of dip will be only one, but apparent angle of dip can be apparently many, because there are different planes which are possible. Magnetic meridian is only one. There can be different vertical planes inclined to magnetic meridian. So apparent angle of dip, there will be many, but true angle of dip will be one. It's just like finding soulmate, right? Soulmate will be one, right? That's what usually people say. And I have found my soulmate. That's so. So soulmate will be one, but there will be different crushes, right? So let's continue. So yes, that's it. So we have completed the theory part, and now I have to show you some problems. Then only you will be clearly understanding the things. I'll make the problems in another video because this has already been very lengthy. I'll show you the problems in coming in another video. Okay, so that's all from me. So obviously, in order to understand the concepts of physics, these visualizations are very much helpful. I've shown you the figures and animations of magnetic field and all. It is a very good way of understanding the concepts in physics. Apart from that, another thing which is inevitable is solving many questions. Unless and until you solve different problems, you will not completely grasp the idea. So you have understood 90% of the things. That 10% which is remaining, you will understand by these problems. So these are the questions that we are going to solve in the coming video. So I'll make a very short video on the problems, and with that will be the end of it. So I hope you have liked the video. So you have understood. I hope you have understood everything that I have taught. If you have any doubts, please ask me. And obviously the speed, it will vary according to the audience. So until we meet again, it's goodbye.